This video is about periodic trends. By the end of this video, you should understand what a periodic trend is and be able to explain the trends for each of the following in terms of atomic structure: ionization energy, metallic character, electron affinity, and atomic radius. Recall that the electron configuration of an atom determines many of the atom's properties. Since electron configurations show patterns down and across the periodic table, the corresponding properties they determine will also show patterns. Periodic trends describes the patterns in those atomic properties. We look at periodic trends as we go down a group on the periodic table. Recall, as we go down a group, a principal energy level is added with each successive element. This will affect a number of its properties. As we go across a period, we add electrons to the same principal energy level, again having effects on properties. Let's start with atomic radius. Atomic radius is literally the radius of the atom, or how large the atom is. It's determined by taking half of the value of the distance between two bound atoms of the same element. It has to be determined this way since the electron cloud has no clear boundaries, so it's difficult to know where to stop measuring from nucleus to edge of atom. If we graph the atomic radius for the first 100 elements, we see some patterns emerge. First, let's orient ourselves. Looking first at the points that seem to be in a downward sloping line, these points represent the atomic radius for elements in the same period of the periodic table. This is the first period, second period, third period, fourth period, and so on. Looking at points at the same position of each peak, we see the atomic radius going down a group. These top points would be group 1, the second points would be group 2, and so on. You'll notice then that as we go across a period, atomic radius tends to decrease, and as we go down a group, it tends to increase. This trend is shown here in this diagram. Atoms get larger as we go down a group, and they get smaller as we go from left to right across a period. Here's another visual representing the same trend: the increase in radius going down a group and the decrease in radius going across a period. So let's look at the structural reasons for this trend. As we go down a group, we're adding electrons to higher and higher principal energy levels. Therefore, electrons are getting further from the nucleus. They're then less tightly bound. This causes the atom to expand as we go down a group. Going across a period, on the other hand, we're increasing the nuclear charge since we're increasing the number of protons as we go from left to right across the period. Let's consider the explanation for this trend. Looking first at the down a group trend, electrons are being added to higher and higher principal energy levels, as seen here. As we go from beryllium to magnesium to calcium down the group, our valence electrons are in the second, then the third, then the fourth principal energy level. Since these electrons are further from the nucleus, they're less tightly bound. Likewise, since they're further from the nucleus, the radius is increasing. Going across a period, on the other hand, we're increasing the nuclear charge as the number of protons increases. However, there's a minimal increase in electron shielding because electrons are being added to the same principal energy level. Consider boron, carbon, and nitrogen in the same period. Boron has 5 protons, carbon 6, and nitrogen 7. Therefore, the nucleus is becoming more positive. And we're not increasing shielding very much, since the electrons are all being added to the 2p sublevel. Therefore, the electrons are pulled more tightly to the nucleus due to this increased nuclear charge, thus shrinking the radius of the atom as we go across a period. Using the atomic radius trend, you should be able to explain many of the other trends we're about to look at. Let's consider ionization energy. As you know, this refers to the energy required to remove an electron from an atom. Again, looking at peaks of mountains, we see going down a group, and slopes of mountains we see going across a period. In this case, we see a decrease in ionization energy down a group and an increase across a period. That's shown in the schematic here. Now let's look at the structural explanation for this trend. Recall again that as we go down a group, electrons are farther from the nucleus because we're adding new principal energy levels each time, and these electrons are less tightly bound. Therefore, these electrons are easier to remove. Going across a period, on the other hand, electrons are added to the same principal energy level. The increased nuclear charge from the additional protons overshadows the very small increase in electron shielding, therefore they're more difficult to remove. Metallic character describes how much an element acts like a metal. Metals tend to lose electrons easily and are said to be more reactive. Likewise, metals tend to be shiny, malleable, and form positive ions because they lose electrons easily. Elements that are more metallic will exhibit these properties more strongly. Based on what we know about ionization energy and radius, it shouldn't be surprising that metallic character decreases across a period, since electrons are more tightly bound, and increases down a group, since electrons are less tightly bound. This also means that reactivity decreases across a period and increases down a group. Electron affinity is defined as the energy change associated with the addition of an electron to a gaseous atom. This process is represented by the equation here. This is in some ways the opposite of the ionization energy. Since the addition of an electron is an exothermic process, electron affinity will have a negative sign. A more negative electron affinity means that more energy has been released. It's a more thermodynamically favorable process. The trend for electron affinity is quite messy. However, we can pick up some general trends. We say that the magnitude of the electron affinity increases across a period, meaning the values get more negative, and increases up a group or decreases down a group, whichever you prefer, meaning they get more negative down a group. This is consistent with the fact that elements to the right of the periodic table tend to form negative ions more often than elements at the left of the periodic table. Explaining this trend, as we go across a period, adding electrons makes the atom more stable or lower in energy. Therefore, electron affinity becomes more negative or a larger magnitude. An example is shown here between phosphorus, sulfur, and chlorine. As we mentioned, there's many inconsistencies in this trend. One of the reasons is adding a second electron to a sublevel that already contains an electron will increase electron repulsion. Therefore, the resulting ion will be too unstable to form. Consider, for example, adding an electron to carbon. Since there's room in the 2p sublevel, the carbon minus ion will be stable. Compare this, however, to adding an electron to nitrogen, which already has one unpaired electron in each of its 2p orbitals. Adding another electron causes a pairing of electrons, which is unfavorable since it increases repulsion. Therefore, N- is unstable and will not form. This causes the electron affinity for nitrogen to be lower in magnitude than that of carbon, despite its position on the periodic table. Going down a group, on the other hand, electrons are added further away from the nucleus and are therefore less tightly bound. This makes for a smaller energy change. You can think about this in terms of Coulomb's law. Since distance is increasing, energy is decreasing. Furthermore, more electrons result in increased electron repulsion, making it less energetically favorable to add electrons. Again, however, there are many inconsistencies in this trend. That brings us to the end of this video. Let's review our goals. First, we looked at what a periodic trend is, and then we looked at trends for each of the following: ionization energy, metallic character, electron affinity, and atomic radius.